Okay, everyone, let's get started. So we have our first exam 2 weeks from today. It's October 20th, and there'll be no lecture next Monday. I'm traveling next Monday, okay? So I'm going to go through a review today for the exam, and you'll have 2 weeks to prepare. By the way, is there any issues in the lab? Everything going well in lab? Any questions? Okay, so the exam will cover all the material I've covered up until now except for the branch instructions, branch and jump instructions. So that'll include the RISC-V ISA, where I may ask you to write or analyze snippets of code, translate between C and RISC-V, the various instruction types that we covered in class, R, I, U, B, and J types. And, oh, sorry, I have control, but I actually have control hazards on there. Okay, sorry, scratch that. It will cover the branch and jump instructions because I basically finished that. There's a few things I need to finish on that topic, and I'll get through that today. Then microarchitecture, I'll ask you some questions about control signal and data paths. Then I may ask about fixed point arithmetic, logic circuits, combinational versus sequential, and the 4 logic values that we have in System Verilog and what they mean. Hardware description language, behavioral versus structural, just basic concepts there. And then System Verilog, we covered kind of a small portion of System Verilog, but enough for us to build the CPU out, and we got through all the major topics there. So simulation, reading waveforms, modules, continuous assignment, numbers, how to represent like scalar constants in the code, a bit manipulation, that would be like bit duplication, bit slicing, and bit concatenation, reduction operators, that's where you have like, you can take a multi-bit signal and reduce it to a single bit. Then we had the always statement, which is used for both combinational and sequential logic. And then there's the sensitivity list that's attached to that. The always com doesn't have an explicit sensitivity list, but it has an implicit sensitivity list, whereas any of the signals that are treated as inputs in there are part of the sensitivity list, right? But basically, the sensitivity list is what activates an always statement. Any of the signals in the sensitivity list change, the always statement triggers. Default assignments for combinational logic with if statements in always statements. That'll become relevant for your CPU design, for your control unit. You want to make sure that you assign all of the outputs in every control path if you're making combinational logic with an always statement. So that's important when you have like a big complex if then else statement. Case statements, sequential logic, blocking versus non-blocking assignments, registers and RAMs, and test benches. So quiz 3 was due on Friday, which had some questions similar to the type I'll have on the exam. So the first question is, consider the RISC-V microarchitecture shown below. What's the value of reg-write WB, ALU source EX, and reg-select WB when the following instructions are in the following pipeline stages? So in this case, I'm showing kind of a slightly confusing view, but this is the architecture, this is the microarchitecture, showing essentially what the control signals do, what they're plugged into. And the CPU is shown as these 2 separate diagrams. Of course, in reality, they're part of the same CPU design. And so I'm saying that in the fetch stage, we've got a mul-h instruction. And remember that the fetch stage is just essentially the program counter and the instruction memory. So if the mul-h is in the fetch stage, it just means that the address of the mul-h is currently sitting on PC fetch. And we're in the process of reading the contents of that address out of the instruction memory. And then in the decode EX stage, we have the LUI instruction. meaning that that instruction has use of the ALU and the register file read ports and the control unit, and then in the write back stage we have an XOR instruction, which means that it's just in the process of writing its result back to the register file. So in the code, the part that used to really confuse me about this is that if you look at the code, the order of these instructions is going to be reversed, because the XOR instruction is the deepest in the pipeline, which means it comes the earliest, which means that if you were looking at this program, the XOR instruction would come first, then the LUI instruction, and then the mol-H instruction, right? So they're shown here in like the opposite order that they would appear in the code. So the question is, what is the reg-write WB? So because we have the WB suffix on there, it means that that represents the XOR, or that control signal is attached to the XOR, because the XOR instruction is in write back, and this is a write back signal. And the signal is reg-write, which is determining whether that instruction is writing to a register. So the XOR is writing to a register, and so the reg-write WB should be 1, right? The ALU source EX determines what the second input on the ALU is for whatever instructions, in this case in the EX stage, because the EX suffix. So that's the LUI. ALU source EX is going to be 0 for an R type and 1 for an I type, and you don't have to memorize that. You can tell from tracing the ALU source signal, which I've got circled here on the right diagram. This signal controls the MUX that controls the second operand going in the ALU. The first option, or the first input in that MUX, is coming from the reg file, which would be for an R-type instruction, and the second input is coming from this sign extended immediate. So ALU source EX should be 0 for an R-type instruction and a 1 for an I-type instruction. But actually there's a third option that's not explicitly shown here. The third option is if I don't care because I'm not using the ALU. And in this case, that's exactly, no, sorry, that's not true. LUI is in write back. We have a mol-H in decode in EX, right? So the mol-H is an R-type instruction. So the ALU source should be a 0 for that, right? Now, if the LUI was in the execute stage, then it wouldn't really matter what the ALU source is, because the ALU is not used for the LUI instruction. Now you might say, well, how does that determine? If the output of the ALU is not used for anything or is ineffectual, then any of the inputs to the ALU are a don't care. And the way that you would make the ALU output not used is if you don't select its output in this MUX here, reg select MUX, right? So if the reg select MUX is not selecting the output of the ALU, then the ALU inputs are don't cares, right? And so now the thing that's a little confusing about that, though, is that that MUX actually comes in the next stage, right? So the output of the ALU is actually used in the sense that it's put in the pipeline register, but then in the next cycle, the output of that register can just be ignored because it doesn't get selected as part of this MUX. Does that make sense? Okay, so anyway, the point is that for this question, ALU source is 0 because we have a multiply in the execute stage, and multiply is an R type. There is no I-type multiply, right? No, there is no multiply immediate in RISC. I don't know why there isn't. There could be. You could add one, but then it wouldn't be compliant with the RISC-V architecture, right? And then reg select write back. So again, reg select write back is the controlling this reg select mux for whatever's in the write back stage. In this case, it's LUI. So LUI is supposed to do what? It's supposed to select this weird 20-bit immediate value coming in here, the instruction EX bits 31 down to 12. So those come in, they get registered, and then in the write back stage, whatever that was, whatever that is will be what it was in the previous stage, right? So that pipeline register will delay that by one cycle, and then setting the reg select mux to 1 will select that. So reg select should be 1, right? Not just, well, technically 0, 1 because it's a 2-bit signal. Okay? All right, then question 3 was pretty much the same thing, but with different instructions. So reg select, reg write write back would be a reg write write back. Reg write write back. So the write back is CSRW. So CSRW, I mean, in RISC-V, that always does write back, right? But in our CPU, it only writes back if you're reading the switches, not if you're writing the hex displays, right? So I don't remember what the right answer to that was. I guess it's probably 1, right? I have to double check that. You guys with me? So reg write write back is whether you're writing a register, a general purpose register, for whatever instruction is in the write back stage. That's CSRW. So the question is, does CSRW write a register? And in RISC-V, in general, the answer is yes. Our CPU, you don't have to if you're writing to hex displays. ALU source EX would be a 1, right? Because there's an add I, that's an I type. And reg select write back would be, well, again, this is weird because the reg select write back, if you have CSRW and write back, then you're probably going to want to select the switches, right? The I/O, the input, the GPIO in, which would be a 0 for that. Make sense? Okay. Now, actually, yeah, yeah, that makes sense. Okay. How many cycles is required to perform a write to synchronous RAM? 1. What's the result from performing the RISC-V mol H instruction on input values 1111 and 0001, assuming the registers are 4 bits wide? So if this were a 4-bit microprocessor, then you'd multiply 2 4-bit values to get an 8-bit product. The mol H would give you the upper 4 bits of the product, and mol H is signed. So the first number is -1, right? All ones is -1 for signed, for a signed value, or when interpreted as a signed value. And 1 is 1, so -1 times 1 is -1. And so, right, the upper 4 bits should be 1111, right? Make sense? So 1 times -1 is going to be -1, meaning 8 ones. So the upper and lower bits of the product would be all 1s, right? So mol H would give you all 1s. Okay, right, so that was the quiz. And then I thought I'll go through the exam I gave last year, just to give you an idea of the questions I'll ask. So I'll run through these pretty quickly. Let me know if you have any questions about these. Now, last year, I gave the exam online, so it was multiple choice. This year, we're going to do a written exam because the department as a whole are moving back towards written exams. Just because it's, you could just put these questions into like ChatGPT and it will give you the answer. So obviously, the exam this year will be, I'll have some, fill in the blank or maybe have you, write something short. It won't necessarily be multiple choice, but these questions from last year were multiple choice. But the questions will be very similar. So assume our core CPU design shown below has a bug where the wire labeled regselect-EX could only be driven to the value of 1, or 0, 1, because it's a 2-bit. Which of the following instructions would still execute correctly despite this broken signal? So if regselect is 1, then that would force the register file to only get, remember regselect is selecting this mux. What's going in this thing? The immediate, right? So pretty much if the regselect was kind of hardwired to 1, that would mean that we would always write the immediate, the 20-bit immediate, into the register file, which means the only instruction that would work would be an LUI, right? The other instructions would be broken, but the LUI would still work, right? So the answer there would be 5. Which RISC-V instruction would multiply the value stored in register 4 by 16? This is kind of more of a 212 question. But I put it in here to highlight the difference between the MIPS and the RISC-V shift instructions. So if you want to multiply with a shift, then you shift left, and the value, your multiplier would be 2 to the power of how many bits you're shifting. So if you take the log base 2 of 16, you get 4, which means you have to shift by 4 bits, right, to multiply by 16, and you're shifting left. Now, all of the answers are shift left. They're all shift lefts. So which one is the right one? Well, that actually depends on what, if you're in MIPS, the MIPS correct answer in MIPS would be SLL X4 X4 4. But in RISC-V, it would be SLLI X4 X4 4. This is really obscure. Probably not a great question, but in RISC-V you have to do a shift. So in MIPS, the default shift was an immediate shift, and if you wanted to shift by a variable amount, you had to use the V option, SLLV, shift variable. But the RISC-V guys thought that that was ridiculous because they thought that if you're shifting, it's more often the case that you'd be shifting by a variable amount, not a constant amount. I don't know if that's true or not, but they made it so the default shift is a variable shift. And so if you want to shift by a constant amount, you have to use the shift immediate instruction. Does that make sense? So anyway, and this one here is shift left arithmetic. That one doesn't make sense because the shift arithmetic really only applies to a right shift. Now, sometimes you'll still see shift left arithmetic, like in Verilog, for instance, but that's only in cases where the shift amount can be negative. So if you shift left by a negative amount, you're really shifting right, so you should support shift left arithmetic in that case. But we don't support, let me make sure here, let me think about this. Does it? No. RISC-V doesn't support negative shift amounts. I don't think so. I should confirm that, though. MIPS didn't. RISC-V might. But no, I don't think so because there's no arithmetic left shift. No, so I don't think it does. No. So in the assembly code, you can only shift by an unsigned amount, right? 0 or positive. Okay. Anyway, any questions about that? Okay, which code is equivalent to the code below? So this assign f equals a ternary, nested ternary. And so what's happening here is that you'll notice that if x is 0, 1, the output is 1, 0. If x is 1, 1, the output is 0, 0. If x is 1, 0, the output is 0, 1. And otherwise, the only other possibility here is x being what? 0, 0, right? In which case it assigns it to 1, 1. So it looks like we're basically just doing a bitwise complement here, right? Whatever x is, we're just going to flip each bit, both bits. But we don't really have that here. We have an assign f equals x XOR 0, 0, which has no effect at all. There's assign f equals x bit 0 concatenated with x bit 1, which is flipping or swapping the two bits of x, so that's obviously not what's going on. This fourth option checks to see if x0, x bit 1 and x bit 0 are equal, in which case it complements them, otherwise it doesn't, but that's not what's happening here. So the only possibility is this first option, which says x nor 1, 1. And it turns out if you x nor, sorry, if you, sorry, not x nor, nor. If you nor something with 1, it just complements it, right? So x noring with 1, 1 is a bitwise complement. You could have also XOR'd with 1, 1. So if you, sorry, if you nor with, I think I said that wrong, let me say that one more time. If you nor a value with 1s, it complements, does a bitwise complement. Likewise, if you XOR with 1, 1, it will also complement it, right? You guys follow that? Does it make sense? So this is kind of a 211 question in a way. But yeah, the point is that I think the synthesizer will generate the same hardware for both statements. They're both equivalent. Okay, when a program is being executed on the 3-stage RISC CPU, in what stage is the 6th instruction when the 3rd instruction is in write back? Okay, if the 6th instruction, if the 3rd instruction is in write back, it means the 4th instruction is in execute, which means the 5th instruction is in fetch, which means the 6th instruction is nowhere, hasn't been fetched yet, right? So it's not yet fetched. Assume the following Verilog module, fill in the missing values for the test vectors for testing module AAA. So, so this takes 2 copies of A and concatenates it with B. So if A is, so if A is 0, I'm going to take 0, 0, and add B, which is 0. So likewise, 0, 0, 1, 1, 1, 0, 1, 1, 1, right? So the answer is 0, 1, 6, 7. 0, 1, 6, 7, yeah. See that? So I just converted these binary values to decimal because we're using decimal here in the answer. So 0, 1, 6, 7. Does everyone make sense? All right. Assume the following Verilog module. How many total bits comprise the inputs to module AAA? This one's easy. Just clock, reset, and then we have a nit, which is not 1 bit, but 3 bits there, right? So it should be 2 plus 3, 5 bits, right? Consider the RISC-V microarchitecture shown below and assume the following instructions in the corresponding pipeline stage. What statement is true? Okay, so we've got mul H being fetched, LUI being decoded and executed, and an XOR in write back. So it says PC fetch contains the address of the instruction in decode EX. Well, that's not true. PC fetch contains the instruction of the instruction in fetch. Or sorry, PC fetch contains the address of the instruction in fetch. So that's not true. ALU source EX is a don't care. Okay, so the instruction being executed is an LUI. So yeah, the LUI doesn't use the ALU. So yeah, ALU source is a don't care. So 2, I think, is good, is correct. ALU op EX must be set to 1000. I don't know, and without seeing the ALU op table. Do I have that? No, I don't have that. I would give that to you here if this were a question. I don't have that memorized, so I don't know about number 3. And reg write EX is set to 0. Reg write EX would be determining whether the instruction EX writes the register file, which it does, because it's an LUI, so that one's not true. So it looks like the answer is 2. Which of the following is a problem with the module below? So it's just pretty much just an always COM in there. So option 1, the signal assignment statements have 4 bits on the left side and 3 bits on the right side. So yeah, that's true, right? Because A and B are both 3 bits, and we're doing bitwise operations on them, right? You know, bar and ampersand. And so on the right-hand side, we would have 3 bits, and C, which is on the left-hand side, has 4 bits. So yeah, that's a problem. I don't know how, I couldn't tell you off the top of my head how Verilog deals with that if it would give you an error or if you just get like an X in the upper most significant bit of C. I don't know how. I'd have to run that through. I don't know. I have to run it through ModelSim. Two, blocking assignments are improperly used within an always block. No, actually that's correct because, well, the convention is to use blocking inside of a combination of logic. So that's fine. Blocking, of course, is just a single equal sign. C is double driven. No, it would be double driven if you had assign statements for C. If you were assigning C in a continuous assign statement, right? But because they're both of these assignments to C are in the same always block, it's not double driving. Basically, the first assignment is a default statement, right? So this is just the thing that's confusing about Verilog is that it's fine here because the only one that matters is the one that happens last in the always block. So if B was 0, then you would assign C equals A or B, and if B is non-zero, then C would get A and B, and that first assignment to C would be effectively ignored, be overridden, right? And then 4 says there's no structural HDL in this module. Well, yeah, that's true, there's not, but there doesn't need to be. Structural HDL is when you instance other modules, right? We don't have any other modules. Instance, it's just an always block, it's behavioral. Okay, and consider the RISC-V microarchitecture shown below. What is the value of the RD write back, reg select write back, reg write EX? RD write back would be, wait, what's RD? Oh, RD is the register destination. Right, that's where we're writing. So RD write back would be the destination from the write back instruction, which is the XOR I. So the answer there is 3, right? We're writing, the register destination is 3. Because we're writing to register 3 in the instruction in the write back stage. Reg select WB, again, it's referring to the XOR I, and that would be, I guess, 2, right? Because it's the output of the ALU is what you're writing back for an XOR I. And reg write EX would be a 1 because there's an LUI in the EX stage, and the LUI does write to the register file. Okay, which of the following system Verilog statements takes as input an unsigned 8-bit value and multiplies it by 3? Okay, this one is technically more of an arithmetic question. Not a great question, but it shows you kind of this is a quick and dirty way to multiply by a constant. So I mentioned that you can multiply by powers of 2 by shifting left, but you don't have to, if you don't want to multiply by a power of 2, like 3 is not a power of 2. So how would you multiply by 3? Well, you have to break it down into powers of 2. So if you multiply it by 2 and then multiply it by 1 and add those together. So if you take a value, you multiply it by 2, and then you multiply it by 1, and you add those together as like partial products, right? It makes sense? So you shift it by 1 bit, and you shift it by 0 bits, and you add those two things together, and it will have been multiplied by 3, right? So that's number 3 here. B. So B equals A with an extra 0 concatenated to the right-hand side. So that's shifted left by 1 bit, and then we add the original value of A. Now you might ask, wait a minute, that would give you, wouldn't those bit widths be different on either side of the addition sign? Yeah. Yeah, but the important thing is that presumably B is, well, I think it'd be fine. If B can either be the size of how many bits A has, or that plus 1. Okay, which of the following system Verilog statements will receive 3 1-bit inputs, A, B, and C, and produce a 1-bit output Y that is true if exactly 2 of its inputs are true? Okay, so number 1 is basically doing a parity calculation. If A XOR B XOR C, which is true when, in this case, if an odd number are set, but that's odd number, that's not exactly 2, so that can't be true. That can't be the case, right? It can't be That wouldn't work. Number 2 says assign y equals a or b or c. That would be true if 1, 2, or 3 of the inputs are true. So that doesn't work. Third option says if a plus b plus c equals 2, then y equals 1, else y equals 0. That looks right, right? If 2 of the input, so we're basically adding all 3 values. We have like a 3-input adder, and if 2 of them are 1, then the sum would be 2, right? Or if 2 of the inputs are 1, then the sum would be 2. So I think that one's good. Number 3. Number 4 is pretty much the same as 1, right? And 5 would be 5 would be true. 5 would give you a 1 whenever an odd number of the inputs are 1, right? Okay, the following system Verilog code will generate a repeating sequence of n values in consecutive cycles. What's the value of n? Oh yeah, this one is this one's tricky. Okay, so the idea here is we want to figure out what the period of this is. This is a linear feedback shift register. So we have this state. So state starts out as 2. So 0, 0, 0, 1, 0, right? 2 in 5 bits. And every cycle, we're going to take the upper 4 bits and shift them down. So 0, 0, 0, 1, right? And then the most significant bit will be replaced by bit 3 XOR bit 1. So this is bit 4, 3, 2, 1, 0. So bit 3 is 0 and bit 1 is 1, so we're going to have a 1 there, right? Okay, so then again, we shift the upper 4 bits down, right? So these 4 get shifted down. And the new most significant bit is going to be 0 XOR 0, so that's a 0, right? Okay, then again, 0, 1, 0, 0, so those guys get shifted down, and we're going to put in a 0 XOR 1, right? So 1. Okay, well, we still haven't repeated yet. Okay, so now 1, 0, 1, 0, 0 XOR 0 is 0. Okay, so we still haven't repeated. 0, 1, 0, 1, and 1 XOR 1 is a 0. Okay, oh, holy cow, we're still going. Okay, 0, 0, 1, 0, and a 0. Okay, there we go. Now we're repeating. Okay, so you can see that we eventually landed back on 2, but it took us 1, 2, 3, 4, 5, 6 cycles. Okay, once we get back to 0, 0, 0, 1, 0, then it's going to repeat that same sequence again. Right? So, yeah, the period of this LSFR is 6. Yeah, ideally the period would be 32, right? Because we have 32 possible values, right? But we're not going to get all 32 possible values out of this thing because I chose this generator poorly. Okay, which input value to the module below is a don't care? Looks like a bit 0 is a don't care because we have bit 1, bit 2, and bit 3, but we don't use bit 0. So a bit 0. Which of the following statements is true? A continuous assignment statement can infer memory? Nope, not true. An always statement is behavioral HDL? That's true. If statements can be used outside of an always block? Nope. A signal can only be read by one always block within the same module? No. Now that's weird because each always block, each signal can only be assigned by one always block, but you can use the same inputs for multiple always blocks, right? So that one's That one's not true the way it's written. And then always blocks cannot be used to design combinational logic. That's not true. So answer is 2. And I think that's the last question. Yeah, and consider the following module. How many cycles of delay exist between signal A and signal B? So signal A, it takes 1 cycle to make its way into A delay 1. It'll take another cycle to make its way into A delay 2. A third cycle to make it into A delay 3. And a fourth cycle to make it into A delay 4, right? So there's 4 cycles of delay here. Now, A delay 4 gets put into B immediately, because that's combinational logic. So that assign statement does not add a 5th cycle. It adds 0 cycles because it's combinational. As soon as A delay 4 updates, then B will update immediately. It'll activate that always. So 4. Answer is 4 cycles. So this is just a classic shift register. Takes 4 cycles to work its way through. Okay, any questions? Okay, cool. Now, one other thing I do also on Blackboard, I have a study guide for the exam on there too. This is probably a little bit closer to the actual exam because of the way it's not multiple choice. It was this was from a year when I gave just a traditional exam. So I'll run through this really fast. If you have any questions, let me know. So this one says identify any problems. This one uses assign statements inside of an always block. There's a with mismatch that we covered earlier. And B is 3 bits and used an if condition. Ah, yes. If B. Can you do that? If B is not a Boolean, if it's 3 bits, yeah, you can do that. It's fine. I don't know. That's not a big deal. Anything non-zero would be considered true in that case. To what value will the system Verilog code be set to signal B when A is 1011? So this is just bit twiddling. We covered one like that. Write a system Verilog module named parity. It receives 3 1-bit inputs. It produces a 1-bit output Y that's true if an odd number of its inputs are true. So we covered this already, something similar anyway. But notice that in this case, I actually ask you to write out a little snippet of code here as opposed to doing a multiple choice. So just be aware I might ask you to write a little snippet there like that one. This one says, consider the design of a 3-stage pipeline CPU shown below. Write a system Verilog snippet to implement the sign extend block. So the sign extend block is over here. So in this case, we're duplicating instruction EX bit 31 is actually the sign bit of the 12-bit immediate, right? So we're taking the 12-bit immediate, that's bits 31 down to 20, and we're duplicating the first bit 20 times, and then the concatenating that to the other 12 bits, right? So we're basically just taking a 12-bit value and extending it out to 32 bits by sign extension. Write a system Verilog snippet to implement the block that produces the GPIO out signal. Very easy. It's just a clocked thing that has an enable. So if GPIO write enable is true, then we'll register the read data 1 EX. Now, notice also here, this is inline code. So in this code, I have to actually use the names of the signals that are in this module, right, as opposed to having this outlined as a separate module. Some of you guys might prefer to do outline, like have this a module, right, where you wouldn't have to use the actual, like here, like I had to use instruction EX31. I actually had to use like the bits of the instruction that map to the immediate field in the I-type instruction. And that's just because I inline this code, right? The assumption is that I'm just putting this in, I'm mixing this behavioral code in with the structural code, right? Is that probably not everyone's cup of tea because you're mixing together structure and behavior together into one blob. But that's more of a, personal preference thing. For the purpose of the test, it's easier to do inline because you just, it's a shorter answer. Okay, this one, I like this one. This is kind of cool. It's kind of tricky though. So in the following table, mark the stage holding each of the instructions listed in the first 4 rows. Use the following abbreviations: fetch, F for fetch, E for execute, write back, and W for write back. Assume the instructions appear consecutively and the first instruction is fetched in cycle 0. Give the state of each of the control signals shown in the last 5 rows in each of the 6 cycles. Use U to indicate an unknown value and X for don't care. So basically in the first, what I'm saying here is first 4 rows, we're just keeping track of what's going on in the pipeline. So the first instruction is fetched in cycle 0, it's executed in cycle 1, and it's written back, it's executed in cycle 1 and it's written back in cycle 2. The next instruction goes through the same pattern, but just offset by 1 cycle, right? So we just have F, E, and W indicating what's going on for each instruction in each cycle. And then below that, we're figuring out what all of the control signals are. So when we're fetching the first instruction, I don't know what's in execute or write back, and all these control signals refer to execute and write back instructions. I don't know, but I don't know what's in there because I didn't show. It's whatever came before the LUI instruction. So I put question marks. Likewise, in cycle 1, I have 2 control signals here that are write back. So I don't know what's in write back. All I know is what's in execute. But the instruction that's in execute is the LUI, so I just fill out what these control signals are for the LUI. So LUI, writes the register, so reg write is 1, reg select is 0, 1. That's the routing the immediate in the register file. ALU source is a don't care because the LUI doesn't use the ALU, and GPIO enable is a 0 because this is not an IO instruction, right? And then once we get to cycle 2, we can finally fill in all of the signals, but you have to pay attention to each one of these signals is in a different stage, so you have to match up each signal with the corresponding instruction based on what instruction is in which stage, which is indicated above it in the column, right? So, if you can answer this question, you can easily do the lab, because this is essentially what you're doing in the lab. It's just solving this problem, but converting it to system Verilog. What changes to the CPU in question 4 would allow the CPU to execute the fictional WRPC instruction, which behaves as shown below. So I'm basically adding an instruction to the repertoire of instructions that writes the current address of PC +1 into register RD. So PC, assuming here is PC fetch, I should have specified that. So how would you do that? Basically you have to get PC fetch into the register file, right? So the reg select mux is what controls what goes in the register file. So you'd have to basically take the PC fetch and run a line from that into the reg select mux, right? Now the question is, though, the confusing part about this is when that instruction is in the write back stage, then the program counter, its program counter would be like PC write back. PCEX would be the one after that, right? So technically, actually this is a bug, this should say PCEX, right? Because PCEX would be, remember the program counter fetch is going to be the instruction that's 2 instructions behind this one. So you're supposed to write, basically what this instruction is doing is it's providing a way to jump to whatever instruction comes after this instruction, right? That's what you're doing. It's basically a link instruction, right? It's like a return address, basically, without doing a jump. So you'd want to connect PCEX into the reg select mux, because the reg select mux is in the write back stage, right? You guys with me? So I'm not sure why I said PC fetch there. It should be, I mean, PC fetch, assuming you had if it was registered, yes, but if you're just going to connect something directly, it should be PCEX. Okay, write a sequence of 2 RISC instructions that would trigger the register file bypass. So basically I'm writing to register 2 and then reading from register 2 in the very next instruction, so that would trigger the bypass. What would happen if the register file lacked write bypassing? In this case, this code sequence wouldn't work, not on our CPU, because, well, it wouldn't work in the sense that the OR-I instruction would be operating on the old version of X2, not the new version of X2 that's calculated by the LUI instruction. Convert the following behavior of the system Verilog into a truth table. It's pretty simple. Just come up with all the values of A and come up with the corresponding values of Y. That's just combinational logic. And write a system Verilog module named minority. It receives 3 1-bit inputs, produces a 1-bit output Y that is true if at least 2 of the inputs are false. Okay, again, that's just Boolean logic. Now, notice in this case I use the bang operator instead of the tilde. There is a bang operator. That's a logical negation. There's no difference between bang and tilde if it's a single bit that you're operating on. If it's multi-bit, though, like say I have a value that's 0, 1, and I do bang, the output of that will be a single bit output, right? Will be basically just 0 or 1. But in the case of single bits like this, it doesn't matter. Tilde and bang are equivalent. Okay, write a self-checking test bench for this module. So I did that. Basically just set the inputs, check the outputs with a delay. Write a system Verilog module named majority that uses the minority. So this is kind of interesting. So this one is creating a majority circuit by leveraging the existing minority circuit. So in this case, I just connected the minority circuit and inverted the inputs. What's the purpose of the sensitivity list in the always statement? It activates when any of the inputs in the sensitivity list change. Right, this is a blocking versus non-blocking. We talked about that. For which of the instructions is the reg-write-ex signal not asserted? Reg-write-ex. Not asserted. Add, subtract, it would be asserted for those, right? So the answer here should be reg-write writes the register file, right? So the only one of these guys that doesn't write the register file, well, there's 2, right? Branch of equal and store word, right? I don't know why that one's screwed up. I fill in the table for the module below. Yeah, so this is just another kind of a test bench thing with a delay. How many total bits comprise the inputs? We covered that. Right, similar to what we already covered that. Describe any problems with the module below. B is double driven here. Yeah, so this one is kind of crazy. Notice how B is double driven because we're assigning B in 2 separate always blocks. So notice these are 2 separate always, right? There's no begin and end here, right? So this would actually be a case of B being double driven. Yeah, and technically it should say output logic B. But in this class, I just tell you to always use output logic, so you don't have to worry about it. In some cases, you don't need logic, but it's safe to just always use it. Describe the process by which a user entered HDL design is converted to a form that may be loaded. Yeah, synthesize, place, and route, generate bit stream, program FPGA. And describe the process by which an FPGA is programmed. Bits are shifted serially into the FPGA to configure all the LUTs, RAMs, etc. Okay, and that's it. Any questions? Okay, all right, so next, let's finish the lecture from last Monday. So we were talking about the branch and jump instructions. So the first issue was addressing. So MIPS uses PC. Yes.
Do we have any like JL and JL?
Possibly. Yeah. 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 That's because this is the. I'll be able to finish those today. Yes. Yes. Yep. Okay, so branch, so normally branch addressing is pretty straightforward, at least it was in MIPS. So you took the program counter, you added the offset times 4 because the offset was in terms of the number of instructions you skip, right? And instructions are 4 bytes, so you multiply that by 4 because the PC normally is byte addressed. In this class, it's word addressed. So in this class, you just, the idea would just be you take the PC and you add the offset and you're done. And that's still the case for branch instructions in RISC-V. The only complication is the offset is like spread all over the place and scrambled. You just have to figure out how to actually calculate the offset from the instruction, but it just involves bit twiddling, bit manipulation. So it's not a big deal. It's not like you have to do any arithmetic. You just have to figure out what the immediate is, and the immediate's kind of scrambled. So we gave you that code. The jump had a similar issue. Now the jump is supposed to go to, in MIPS, if you remember, the jump had a pseudo direct address. So the idea was to put as much of the target address in the instruction as possible, and then you just kind of just shove that in the PC. And any bits that you can't fit in the instruction, you get from the PC. So in MIPS, it was you would concatenate the upper 4 bits of the PC with the lower 28 bits that you get from the instruction, right? Well, technically 26 bits from the instructions and then extra 0, 0, because you have to multiply it by 4. RISC makes this a little bit more complex. Again, the offset is scrambled, and you add to the PC, right? So technically, the jump in RISC-V is also PC relative, but it has a wider offset, right? Unlike in MIPS. Remember, MIPS used pseudo direct addressing for jumps. RISC-V is still using PC relative addressing. But then you get to the jump register instruction, and this one is the weirdest one yet. So this one has a 12-bit offset that you have a 12-bit offset, but you add that to the contents of the RS1. So when you jump register, you have the target address in a register, but you still add a 12-bit offset, right? And then this and, you see this and thing is just there to zero out the last 1 bit, sorry, E, right? So the least significant bit is zeroed. So this will guarantee that the target that you go to is aligned on the 16-bit boundary, right? In other words, the address bit you go to has a 0 in the least significant bit position, right? Okay, yeah, I don't know. It's just another weird RISC thing, right? In MIPS, the branches and jumps all had to be aligned on the 32-bit boundary, but in RISC, they enforce a 16-bit boundary. Okay, so any questions about that? So in order to make it a little easier, we give you the addressing code that you can put in for that. Now, there is an additional complication here, is the fact that you have to stall whenever you get a taken branch or a jump. And the reason for that is if you have a branch that's taken, this only applies to taken branches. What happens is that we are resolving the branch in execute, which is actually not a great idea. That makes execute very expensive because branches have to go through the control unit to set up the data paths. Then you have to go through the ALU to do the comparison for the branch, right? And then you have to go back in the control unit to interpret the output of the ALU to determine if the branch is taken or not. And then you have to then tell the PC source mux to change, right? That's a lot. That's a very long critical path. So if we wanted to make our CPU in this class faster than 50 megahertz, we would have to break that up and resolve branches later. But in the current version of the CPU, we're going to do all the branch stuff in the execute stage. But even then, you have a problem because by the time you get done doing all of that, you have now already fetched the instruction after the branch, the fall through instruction, right? So in other words, in this sequence, if you have an add branch, and then there's a fall through instruction after the branch, when the branch is executing, when it's going through all its stuff, you know, reading the registers and comparing the registers, checking to see if the branch should be taken, at that point, by the time it gets done with all that, you've essentially already fetched now the instruction after the branch. So you have a problem because you don't want to execute that instruction. The soonest you can fetch the target of the branch is the cycle after the fall through instruction has been fetched, right? Which means that the fall through instruction is always going to get into the pipeline, always, even when you take the branch. So you have to live with that. But you don't want the fall through instruction to have any side effects. You don't want it to change a register, and you don't want it to change your hex displays. Because the fall through instruction is not supposed to be executed at all, so you certainly don't want it changing the state of your CPU. So how do you deal with that? When I was in graduate school, they said, oh, you just use a mux that as the instruction goes from the fetch into the execute stage, it's replaced with a no-op, a 0, right? So you basically set a mux up between fetch and execute, and you just steer in a 0 instead of the instruction. Well, it turns out that doesn't work in this CPU because we have asynchronous instruction memory, which means there's nowhere to put that mux because the instruction memory is synchronous. It takes an entire cycle to read the instruction, right? There's nowhere to put that mux. You have to let it read the instruction, right? If you try to put a mux in between the instruction RAM and the register, then the instruction RAM would become asynchronous because you'd have to integrate that mux in with the RAM, right? In other words, you'd have to read the RAM and then mux it, right, at the same time. It would be asynchronous, right? So there was no way for us to do this thing that they told us to do in graduate. It can't be done. So instead, another plan is in the branch, when the branch instruction is in execute, you can have it generate a stall flag. And the stall flag is meant to be sent back to the fetch stage. And then it will get clocked into the execute stage with the instruction. So in other words, the control unit will put out a stall underscore fetch signal. That stall underscore fetch signal will be targeted toward whatever instructions in the fetch stage, right? And then in the next cycle, stall underscore fetch will become stall underscore ex. It'll follow the instruction, right? So in other words, it's like the control unit can send like a poison pill into the fetch stage and then let it pass into the execute stage along with the instruction. So you'll still fetch the instruction. Your instruction ex will still be the fall through instruction, but there'll also be a stall underscore ex signal. And that will tell the control unit to basically ignore the instruction. Or not ignore it, but it'll tell it to ensure that reg write ex and GPIO write enable, which are the only two signals that can cause the state to change in your CPU. Those two signals have to be 0, right? So in other words, the control unit will say, if there's a stall, I'm going to make sure that, the other control signals don't matter, really. It's just the reg write and the GPIO enable is the only ones that matter. Yes?
Directly the control unit set those signals to don't care?
Do you mean the, which signals? The
Register write back.
No, you don't want those don't care because those ones you don't care. Don't care means that the synthesizer will choose what they'll be, and they may end up being 1, right? If you set them to don't care, you may end up getting unintentional right there. So you can set all the other signals that don't care. But you could just put, you know, if you could literally just at the end of your control unit, like just have your whole control unit, and then right at the end say, oh, by the way, if stall EX is 1, then set reg write to 0 and GPIO enable to 0. So that'll override whatever you had set earlier in your control unit. You know, like, so your control unit will set all its stuff, and then you'll have a little epilogue there that'll say, oh, by the way, if it's stalled, don't do anything, don't write anything, right? And that's all, okay? Now, so basically, all you have to do is the execute stage will send a stall fetch back. So stall fetch will be a combinational signal coming out of the control unit, and it will be delayed by 1 cycle to create the stall EX. Very simple, just a 1-bit register always enabled. Make sense? Now, you have to be careful because what some students do is they forget to put this, if you forget this register, there's a pretty catastrophic result. If you don't put this register here, then if you get a taken branch or a jump, the control unit will put a stall out, and then the stall may cause it to change its mind and say, oh, depending on how you design the control unit, you put the stall out, and it'll say, I'm executing a branch, stall, and then the control unit might say, oh, I'm stalling, so this is not a branch. Okay, never mind, and then it deasserts the stall, right? And then it'll say, oh, I'm doing a branch, and then it reasserts it. You'll end up with a combinational loop. So what will end up happening is the control unit will put the stall signal out, which will cause it to deassert the stall, right? Because, and then by the way, that's another thing I forgot to mention. If the stall signal is set, if stall EX is set, then you want stall fetch to not be set. So that's a third thing you want to put in your epilogue. Sorry, I should have mentioned that too. So in addition to the reg write and the GPIO write being 0, you have to make sure that the next cycle you don't stall, right? So if you're stalling now, don't stall next cycle. Never do that, right? Right? But if this is not a common, if you have that logic in there and you don't have a register in the stall signal, then it'll keep changing its mind over and over again in the same cycle. It'll say stall, oh, don't stall, stall, don't stall, stall, and it'll oscillate, right? It'll create an infinite loop of events that trigger in the simulator, right? So this will create a, you know, and if you were able to synthesize this, which hopefully you won't be able to because the if you create an always COM for your control unit, the compiler will catch this, right? But if you put always at star, then the compiler won't catch this, and you'll end up with this combinatorial loop, and QuestaSim will just lock up because QuestaSim is strangely unable to detect loops, which you think it would be, but it doesn't. It'll just lock. It'll just it'll just hang. Okay, so that's one change you want to make. So basically, every time you hit a jump, you have to stall. Every time you hit a branch, you have to stall if only if the branch is taken. If the branch is not taken, then you don't have to stall, right? The branch is not taken, the branch essentially has no effect, right? It acts like a no-op itself. The branch is taken, then you're going to execute a no-op as the next instruction. Okay. Okay, now, one of the other things here is, so the other thing they changed from MIPS was, in MIPS, some of the jumps were jump and link, and other jumps weren't. In RISC, they said, make everything jump and link. So every jump instruction will now link, meaning that it writes to the register file, it writes a link address, a return address, right? Now, when I first saw that, I was like, oh my gosh, that's horrifying. Like, what if I just want to jump? You just set the link address to 0, write to register 0, which you're allowed to write to register 0, but it has no effect on anything, right? So if you don't want to link, you set the link address to 0, but every jump instruction has a link address, which means that you have to have a data path between the program counter and the register file. And I mentioned this during I had a question on the exam last year about this, or a couple years ago, the older exam. So the program counter needs to be connected now to the third input on your reg select mux. And which program counter? It would be the program counter EX, because it would be the delayed form of the program counter fetch. So the idea is that you want the address of the instruction after the jump to be put in the register file. So when the jump is in the write back stage, the fall through instruction, which by the way is a stall now, it's a stall, but it still has an address, right? The fall through instruction is not being executed, but it has an address following it through the pipeline, which is the program counter. So that would be the program counter EX. So remember, you have program counter fetch, and there's a 1 cycle delay where that moves into program counter EX. So in other words, when the fall through instruction, which is stalled, is in the execute stage, its program counter is going to be written into the register file when the jump is in the write back stage, which is why the PCEX is being routed in here. Now you might say, well, that looks weird because everything else going in here is a write back signal except for the program counter EX. Yeah, and that's by design, right? Because you don't want to link to the jump itself. That would be awful, because if you did that, then when you link back to the jump, you'll end up jumping again, right? You want to link back to the instruction after the jump, which was the fall through. That's your return address. That's how you return from your method. Like when you type return in C, that's how that's implemented. Okay, so very simple. You have an extra slot for that, so you just wire it in and you're good to go. Okay, so to summarize, now this is for lab. What I'm talking about now is lab 4. You don't have to put this in lab 3, but now the lecture is ahead of the lab a little bit. I've gotten a little bit ahead. I've gotten to the point where, you know, for a while I was behind the labs, now I'm ahead. But for lab 4, you're just going to add these branch instructions and jump instructions, at which point you'll have the ability to call functions and implement if statements and loops in your code. In fact, I'm not a theory guy, but I think that means you can, I think at that point your CPU is Turing complete, meaning you could take any program and convert it into, you could represent it as these set of instructions and run it on your CPU. You'll have a fully operational CPU, even though it doesn't implement all of the RISC-V instructions, but it has enough to run any program on it. So what do you have? This slide shows a list of things you have to change on your CPU. So you have to add the branch address, JAL address, and JALer address. These are effective addresses, right, that I gave you the code for. You have to make those possible next states for the PC fetch. So this, you know, basically you have to add a PC source mux. You have to add a PC source control signal that controls that mux. You have to add the stall fetch and stall EX as signals. The stall fetch is driven by the control unit, and the stall EX is just a delayed form of that. And then you have to add PCEX as the fourth input to the reg dest mux. That's not a lot of changes. That's pretty simple. And of course, you have to add the control unit code as well, right? That's probably the hardest part. Yeah, and that's it. So that's really the only hardware changes you have to add to implement those guys. And then the other thing is the branch resolution. So the Hennessy and Patterson textbook said that you should have a separate module for branch resolution. So the way they did it was the control unit would send out a signal telling another controller if it was a branch instruction, and then it would give control of PC source to that separate unit. I think it's easier to just create one monolithic control unit, so you can put the branch resolution in your main control unit just as part of your if then else, right? You have to be a little bit careful about how you structure that, but basically you just set up the branch instruction, set up the data paths if you have a branch instruction, and then you have the ALU outputs connected back to the control unit. And so if you do a branch if equal, you tell the ALU to subtract, and if the output from the subtract is 0, meaning that A and B are equal, so A minus B is 0, then you take the branch. Likewise, if you're doing a branch of not equal instruction, you do the same thing, except you just use, you know, the complement. You complement it. You guys with me? If you do branch of less than, then you just use the set less than operation on the ALU, and you check the result to see if it's 1. And if you're doing branch of greater than or equal, then it's just the inverse of the less than. Yeah, makes sense, right? Notice there's no branch of greater than. There's no branch of greater than instruction. MIPS had that, but RISC doesn't. And the reason RISC doesn't is that branch of greater than is hard to implement because we don't have a way to resolve that. Right? But you don't need to, because you could just do a less than and swap A and B, right, in the code, right? You could, in the assembly code, if you want to do greater than, you just do set less than, you do branch of less than and just take the two registers and swap them, right? But so basically, this is a case of where we're going to rely on the software for branch of greater than, but we have branch of less than, branch of greater than or equal, and so forth in here. Okay, so there's six branch instructions. Okay, so now this part is, it gets a little weird though when you test your code though, because how do you test a program with branches and jumps? Well, the way that we tested our program before was you basically just looked at the register file, right? You looked at the registers. But now, what are you going to look at for testing? Well, you have to look at the program counter. You have to look at the sequence of program counters. But you have to also understand that all the branches are delayed. So if a branch is taken, the program counter will not react to that until one cycle later. So let me give you an example. So here's a test program we want you to use. When you look at the fetch sequence, we're going to fetch instruction 0, 1, and then we get to 2. And 2 is checking to see if register X4 and X5 are equal. Are they equal? No, because I loaded negative 1 and 2 in there, right? And negative 1 doesn't equal 2. So that first branch is not taken. So then we're going to go to 3. And 3 says branch if not equal, X4, X5. Obviously they are not equal, so we're going to take that branch, but it's delayed. So the program counter will actually go to 4, which is the fall through, before it goes to the target, which was target 3, it says 8, right? So if you come down here, this is the correct fetch sequence. 0, 1, that's the load immediates. 2, that's the branch if equal that's not taken. 3, that's the branch of equal that's taken, but then we go to 4, which is the stall. And then we go to 8. 8, why 8? Because we're going to target 3. Target 3 is 8. So we go to 8. Target 3 is a jump and link. Means that we go to target 1, so we're going to go to 4. But not before we have the stall, right? So it's going to go 8 and 9. 9 is the stall after the jump and link. Then we go to 4, which is the target. That's target 1. That's when we go to target 1. That's another branch instruction. Is that one taken? Is negative 1 less than 2? Yes. Okay, then that's taken. But again, it's delayed. So we're going to go 4. That's the branch that's taken. Then we go to 5, which is the stall. Then we're going to go to target 4. Target 4 is 9. 9 is another branch, which is not taken. We're checking to see if negative 1 is greater than or equal to 2, which it's not. So that's 10. Is that right? I lose track. 5. Wait, hold on a minute. I screwed that up. So, sorry, 8 is the jump and link. 9 is the stall. Then we go to 4, which is target 1. That one's taken, so we go to 5 is the stall, and then we get to target 4. That's the jump. Ah, yes. Sorry. Yeah, that's where I screwed up. Target 4 is the jump and link register. So that's going to go to 1. Now here's where things get even weirder. What's in register 1? Register 1 is the link address from the prior jump and link that we did when we were at 8. So we're going to jump to 9. we're at 9. We're already at 9, but we're going to jump to, it's jumping to itself. But not until it stalls, not until after it stalls. So check this out. We go 9, and we're going to jump to 9 again, but not, we have our stall. So we're going to go 9, 10, which is a stall, then we go back to 9 again, and then we go to, that one jumps again, and we get another stall there at 10, and then we go to 10 again, okay? So the sequence gets, you have to trace this, you have to trace what's happening in this program, and you have to account for all the stalls, and keep track of where the PC is going. So that's the test program for this one. And then that's test program 1. Test program 2 is where we're going to run lab 1, the lab 1 that you wrote, the square root program. So we're going to combine the binary to decimal converter with lab 1, which will allow you to put a number in on the hex displays. Your code will calculate the square root, convert it to base 10, and then display it on the hex display. So you'll have a fully working like calculator where you put an integer number in, it calculates the square root, which is going to be a fractional number more than likely, and then it will display that fractional number as a base 10 fractional number on the hex displays, right? So that'll be, I'll talk more about that in the next lecture, but that's essentially, that'll take us to the end of the semester. Okay, any questions? Okay, so remember that we have, next lecture is canceled, so you can take that time and work in the lab. And then we'll have the exam on the 20th in class. And then in the next lecture after that, I'll start covering some conceptual material that'll just be basically tested on the final exam. And the rest of the semester in lab, we'll be working on lab 3 and 4. Okay? Okay, thank you.